So we're going to do U-substitution with definite integrals that have limits of integration. Okay, so we know that a definite integral looks like this. It's the integral from a to b of f of x dx. That's what a definite integral looks like, right? Where the limits of integration, excuse me, the a and the b are in terms of x, aren't they? So with a dx, f of x dx, that tells me that my limits of integration are x values. So what we're going to do when we do the u substitution is we're going to change that f of x to be a u, right? And it's not going to be a dx anymore. It's going to be a du, isn't it? So these limits of integration, are no longer x values. They have to be u values. They have to be in terms of u. So that's the only new thing from today. So we're going to keep practicing doing the u substitution, but we're also going to say, okay, if it's a definite integral, how do we do it differently from when it's an indefinite integral? Okay. One of the big thing is we're going to have to change our limits of integration. Instead of being in terms of x, now they have to be in terms of u, which isn't hard. We just have to remember to do that. Okay. Let's look at an example. We're going to do the integral from 1 to 3 of 1 over 5 minus x dx. I'm glad my touch is working. It wasn't working last hour. I was getting very frustrated. Okay. So I see an inner function. Who sees the inner function? What do you see? 5 minus x. Good. So we're going to let u be 5 minus x. And then we're going to take the derivative of both sides. We're going to practice our u substitution today. That's what we're practicing. Oh, we're going to do that Monday too. All we're doing Monday is practicing u substitution all day. Okay, so if u is equal to 5 minus x, what is du equal to? -1 times dx. Good. Okay, so I'm looking over at this integral, and I don't see a -1 in there. I just see a dx. So I need to divide both sides by -1, don't I? So I'm going to divide both sides by -1. So I get -1 times du equals dx. So when I go back over to my integral, instead of a dx, I'm going to replace it with -1 times du. Notice I always put my constant on the outside. Notice that? And instead of 1 over 5 minus x, I'm going to put 1 over u. Okay, everybody's good so far? There's our u substitution. Now we're ready to do what? What do we do next? The antiderivative, right. The antiderivative of 1 over u is the ln of the absolute value of u. And normally, yesterday, oh, we forgot the negative on the front, right? Bring down your -1. Bring down your constant. Normally, with yesterday, if it was an indefinite integral, we would just put a plus c, right? But we're not, and then we would substitute back. But we're not going to do that today. We're going to remember that this is a definite integral. So I need to say, okay, I changed my integral to be in terms of u now. So I have to change my limits of integration to be u values. 1 and 3 are x values, values of x. We need to change them to be u values. So u is equal to, this is so easy, 5 minus x. So the first one was 1, right? My lower limit was 1. So u is equal to 5 minus 1, that's 4. Y'all see what I did? And then the upper limit was 3. U is equal to 5 minus 3. That's a 2. You see how I changed my limits of integration to be in terms of u? You just use what u is equal to and plug in the x and see what you get for u. That's all you do. Okay, so let's go back. What's the problem here? The lower limit is higher than the upper limit. That's exactly right. So we know we need to change the sign and flip the limits of integration, right? So the negative in front is going to go away because we want to take the opposite of that integral. So it's going to be positive integral from 2 to 4 of 1 over u du. Now we're ready to find the antiderivative. So we're not going to substitute back. You ready? The antiderivative of 1 over u is the ln of the absolute value of u. If it was indefinite, we would just put plus c, but it's not indefinite. So we know we have to use the first fundamental theorem, right? And we're going to go from 2 to 4. We already changed our limits of integration to be u values. Listen, let me talk slowly. We've already changed our limits of integration to be u values. So we do not substitute back. If we substitute back, then we don't change our limits of integration. I would recommend changing the limits of integration because the computation, leaving it in terms of u, is going to be a lot easier than if you substitute back for a lot of them. Not necessarily this one, but for a lot of them. So we're going to leave it in terms of u. We're going to change our limits of integration to be in terms of u. And now we're going to do ln of 4 minus the ln of 2. Look how easy that was. That's first fundamental theorem, right? That's how we do definite integrals, right? Okay, and then we can remember one of our fancy properties for logarithms that says when it's a log minus a log, I can rewrite it as one logarithm and divide. That's right. So the ln of 4 minus the ln of 2 is the ln of 4 over 2, which is the ln of 2. Okay, let's do it again. Anybody have a question? Okay, let's do it again. We might as well throw some trig in here. There we go. Okay, so we got to look at this for a bit. Sometimes it's not as obvious what my inner function is and what's my outer function, but if we look at it for a second, we have to be able to determine, okay, what's my inner function, what's my outer function, what's my inner function, and remember what you're looking for. Is the derivative of the inner function present in the integrand? Because that's my g prime of x. Remember that from yesterday? I see tan cubed theta. So as soon as I see tan cubed theta, I have to remember that's tan of theta all cubed, right? So if I write it like that, it might help me to see an outer function and an inner function. And so if I'm thinking that tan is my inner function, is the derivative of tan part of the integrand? Yeah. It is. It is. Tell us what it is. Perfect, Ethan. Yes, it's secant squared, which is the same as 1 over cosine squared. So the derivative of my inner function is present. So I know what my inner function is now. I'm going to say u is equal to tan of theta. Very good. And my outer function is something cubed, right? So du is equal to, we're going to put 1 over cosine squared theta times d theta. And the only reason I'm writing it like that, because that's what it looks like in the integrand, okay? Okay, so then I'm going to go back over to my integral, and I'm going to substitute, because I see there's the d theta, there's the 1 over cosine squared theta. So instead of all that, I'm just going to put du. Everybody's good with that? Okay, and then instead of tan of theta cubed, I'm going to put u cubed. Doesn't that make it a lot more simple? So that's what the U-substitution is meant to do. It's just meant to make finding your antiderivative a lot simpler, and it works. Okay, so now we have to change our limits of integration, remember, because those values were theta values, right? But we're no longer in terms of theta, now we're in terms of u. So we need to say, all right, u is equal to the tan of theta. So u is equal to, let's do the lower limit first. Tan of 0 is 0. And the tan of pi over 4 is 1. Good. Well, that makes it better, doesn't it? Okay, so now we're ready to find the antiderivative. The antiderivative of u to the third is 1/4 u to the fourth. And remember, normally we'd put a plus c and then we'd substitute back. If it's indefinite, that's what you do. But if it's a definite integral, you're going to do fundamental theorem. So you're going to say it's from 0 to 1. Notice I'm not substituting back. I've changed my limits of integration to be in terms of u. So I do not substitute back. Leave it in terms of u. It makes the math a lot easier. Trust me. So this means we want 1/4 times 1 to the fourth minus 1/4 times 0 to the fourth, which is 1/4. Any questions? Now I'm going to give you one to do. If I can find a good one. I'm sure I can. I've got all these problems here that I want y'all to be able to do. Hold on. I'm coming. Oh, here it is. I was like, where's the one we did in the other class? Here it is. Okay. So this is a good one. Everybody's okay? Notice we don't substitute back. It's a definite integral. We do fundamental theorem. We do the integral from 1 to 4 of the cosine of the square root of x divided by the square root of x. Okay, I'll give you all a couple minutes to think about it. We're looking for an inner function and the outer function, and if you decide what the inner function is, then you're going to say, okay, is the derivative of that inner function present in the integrand? It needs to be. My allergies must be bad because my ears keep popping. Like I'm all white. Are we having trouble finding the inner function? Well, I see cosine of something. Do you see it? So think to yourself, could the square root of x be my inner function? What's the derivative of the square root of x? Almost. 1/2 x to the negative 1/2, which would be 1 over 2 square root of x. I see 1 over square root of x. I just don't see the 2. And y'all remember what I said? As long as the variable part is there, it's okay if the constant's missing. So the derivative of x to the 1/2 is there, isn't it? X to the negative 1/2. I see it. So let's let u be the square root of x and go from there. Oh, my back hurts. Oh, this is a good one. We could do this one. We have time. Brendan, you got it? You think so? Remember, we're not worrying about simplifying anything. Sometimes we get ugly values that we don't know, right? And we just leave them like they are. Brought my rain jacket today. I was prepared. Mary drove me to school in the rain this morning. We made it safely. We made it safely.
Why would you do that?
Because she always tells her to speed up.
In the rain?
Not in the rain, but it's raining today. It's different.
And it was dark.
Chill out.
Y'all ready? Does anybody have something they think is right? Is anybody feeling confident?
Maybe.
Diana? Diana, you okay back there? Brendan, tell us what you got.
2 sine of 2 minus 2 sine of 1.
2 sine of 2 minus 2 sine of 1. Ty's doing a dance over there. I don't know what that meant.
The dance made me happy. Not too much. That's his correct.
Okay, so let's see. du is equal to 1/2 x to the negative 1/2 times dx, right? What am I going to do with that 1/2? Multiply both sides by 2. So 2 du equals, look what I'm going to write, 1 over the square root of x times dx. Do you recognize it now? Go back to the integral. We're going to substitute. Instead of 1 over the square root of x dx, I'm going to put 2 du. And instead of the cosine of the square root of x, I'm going to put the cosine of u. Okay, and now I'm going to change my limits of integration. So instead of a 1, what am I going to put? The square root of 1, which is 1. And instead of a 4, I'm going to put the square root of 4, which is 2. Okay, now we're not going to substitute back. We're not, after we find our antiderivative, we're not substituting back. We're not putting a plus c. We're doing fundamental theorem, okay? Because it's a definite integral. So I'm going to bring down my 2. The antiderivative of cosine is sine of u from 1 to 2. So it's 2 times sine of 2 minus the sine of 1. Good job, Brendan.